problem 2.2 says that we want to show that E must exceed the minimum value of potential, V of x, for every normalizable solution to the time-independent Schrodinger equation. And then it wants to know, well, let's not worry about what else it asks. Let's just sort of prove this first sentence first. And the hint is that we want to rewrite the time-independent equation, which is equation 2.5, in the following form. So from here, it says that if E is less than the minimum value of the potential, then psi and its second derivative always have the same sign. And from here, it wants us to argue that such a function cannot be normalized. And I'm not entirely sure why Griffiths classifies this as a one-star problem, because they have pretty much given us sort of the answer in its hint. So let's just analyze the scenario where E does in fact have a value less than V min. Let's just call it V sub m. In this case, V subtracted by E, or V min subtracted by E, is going to always have the same sign as the second derivative of psi. So if we look at this, E is less than V min, so this is always going to be greater than 0. And as a result of that, d2 psi over dx squared, as a result of this, the second derivative of psi with respect to x squared is going to be proportional to some constant c times psi, where c is greater than 0. Because here v minus e is positive, 2m over h bar squared is also positive. Therefore, this is all just some positive constant c. So as a result of that, if we sort of have a scenario like this, the only possible graphs that we can get when we have this condition is one that starts at the top quadrants and sort of slopes upwards exponentially forever, and another one which starts at the bottom quadrant and slopes downwards forever, or curves exponentially downwards forever. Because remember, the second derivative determines sort of the concavity of our function. So if the concavity is always the same sign as the value of the function itself, then if the function is positive valued, it can only ever be concave up, and if the function is negative valued, it can only ever be concave down. So as a result, sort of these two resultant functions go to positive and negative infinity respectively, and if we take the magnitude squared of this, that's still infinity. So as a result of that, these functions are not normalizable. Now, let's look at sort of the final statement. What is the classical analog to this statement? And what Griffith is getting at here is that this result should be sort of a very comforting fact for us, because sort of the same rule is also true in classical mechanics, and the fact that this rule holds in QM means that sort of there is a point of comparison between the two fields of physics. So let's consider a classical case where we just have, a ball sort of on like a flat plane. Well, the energy of this ball is going to be determined by the kinetic energy K added with the potential energy V. And we have a few constraints. Kinetic energy sort of is always greater than 0. It's greater than 0 because kinetic energy is 1/2 mv squared. And v squared means that it's always positive. And then potential energy can be sort of positive or negative or 0. So potential energy is free. So it can be anything. Let's just say any value. So if we look at this condition, well, let's start by looking at the case where, well, it doesn't even matter because k is just some positive or 0 value. And hopefully this sort of equation obviously shows that energy always has to be greater than or equal to the potential exactly. Because k is always positive or 0, and then v is just going to be whatever it is. If k equals 0, then E will always equal v. If k is greater than 0, some positive value, then E is going to be whatever v is added with some positive value, therefore it will always be greater. The E equals v scenario sort of is trivial, because in that case we just get a solution where the second derivative is just 0, and we don't really care about that case, and the case where k is not 0 will always give us a case where the energy has to be greater than the potential. Therefore, sort of this rule carries over analogously from classical mechanics into quantum mechanics. And that is, once again, sort of a very comforting thought, because it gives us it gives us information that, classical mechanics and quantum mechanics aren't completely different. There are at least certain ideas revolving energy in this case, which are shared between the two.